Good evening, everyone. I'm Sonia Zueri of CSV Architects. I'm the project architect and passive house designer of the Salus Clementine project. And I just want to clarify, we didn't win any award yet. We just got the formal pre-certification letter for the project. So Salus Clementine is a 4-story apartment building in Ottawa, offering 42 studio apartments for men and women living with severe mental illness. It's located in the Huron Park area here in Ottawa, and it is slated to be America's largest passive house project and is now considered to be a beacon project for North America. The project is also targeting LEED for Homes Platinum certification. So the design journey for this project has been quite interesting, with a very steep learning curve, as you can all imagine. We started with quite a challenging site. We're in Ottawa, so we're dealing with a seismic zone of magnitude 4 to 5, and the site is east-west oriented and not shaded. The zoning bylaw impacted a lot our design. The required setbacks review dictated the volume of the building, and Ottawa Salus really wanted to make maximum use of the site. So we were able to design a compact building, and to avoid any shape thermal bridging, we stayed away from any cosmetic setbacks in the envelope. Let's take a quick tour of the interior of the building. So we have a heated basement that will accommodate the building services and storage rooms. When we first started, our mechanical designer requested the full western part of the basement to be reserved for mechanical. And luckily, by improving our envelope, we reduced our cooling and heating loads drastically, and the mechanical room also shrank its size to almost half. Our ground floor includes the 6 barrier-free suites and various common spaces. And we were very keen to bring the outside into the common room, and that was one of the architectural qualities we were really striving for. So we're proposing a passive house certified curtain wall system along the south and west sides of the common room, and we're hoping the curtain wall will give us a valuable heat gain in the winter and won't impact our cooling load in the summer. We're also dealing with the recycling and garbage rooms that are located for easy pickup from Clementine Boulevard, but we did not include them in our thermal envelope. Each upper floor is served by an elevator in addition to the stairs, and will accommodate 12 units served by one main corridor. We've made a great effort to minimize all circulation and service spaces. The layout of each unit provides a single open concept living space with a sleeping alcove and a versatile living, dining, and kitchen space. For the structural design, we had to seriously take into consideration the soil's condition. We're working with poor soils, essentially a mixture of silt and clay. And because of that mix, we also needed temporary shoring on the north and south sides of the excavation. Our structural design consists of a light steel structure of light steel studs and joists sitting on a tray slab foundation and foundation concrete walls around the perimeter. The party walls between the suites act all as load-bearing elements, and a light floor topping is specified at the floors in order to reduce the loads to a minimum. At the garbage and parking area, we have a fairly large cantilever of 8 by 8.5 meters, and we could not avoid red steel in that area. So there are 5 reasons we went with light steel. First, easier fireproofing and lower weight on the foundations, a stronger seismic resistance, and the possibility of a panelized system. And of course, the economic advantages were kind of the final reason. And in the end, this decision apparently put us in the first place here in North America, passive house world adventuring a light steel structure. But now let's touch on our envelope. So it was quite challenging to find a passive house grade solution with the light steel frame, and it was easy to focus on thickening the insulation outboard of our light steel structure and straightforward to double, if not triple it, compared to conventional construction. But we were struggling on how to support it. The economics worked in our favor to change our foundation system halfway through contract document to a tray slab foundation and optimize our envelope, where we see even with the tray slab foundation we were able to realize some savings around 30K. And the tray slab foundation system we went with is made of 2 layers of EPS with a vapor retarder membrane in between, and this tray slab system allowed for no thermal bridging and saved a lot on formwork. And actually sandwiching the vapor retarder between the 2 layers of insulation allowed to protect it from any risks of pulling and tearing from the concrete reinforcing. The water table level being above our basement slab level, we had to install a reliable weeping tile drainage system to ensure the insulation is not saturated with water. For the elevator pit, we needed a different approach. It was another 5 feet lower than the basement slab and completely submerged in water at all times. And pumping the water and guaranteeing performance was not as straightforward, and it wasn't economical either. So we're protecting our thermal envelope with a self-adhered high-density waterproofing membrane, and we're protecting our membrane with a sacrificial 3-inch of insulation layer, and that's what you see here on this picture. And this is our tray slab foundation with its different stages of insulation, starting with laying down the granular base, roughing in plumbing and utilities, and leveling the stone and laying down the first 9-inch layer of EPS insulation, installation of the insulation edge elements, and spray foaming around all surface penetrations, and then installation of the 15 mil stego vapor barrier. And we've made sure the stego barrier overlaps the edge elements by at least a foot for a good overlap with our foundation wall. And surface penetrations are then all taped in place. Then our second 3-inch layer of insulation is laid down, and it's all prepped with surface penetrations, and of course spray foam is applied at all gaps, and the edge element were protected with OSB panels just to protect the vapor barrier. Reinforcing steel was then put in place, and the slab was poured in one single pour for like a half a day single pour. So that's our tray slab. For our superstructure, we were indeed like struggling with how to support at least a foot of insulation, and we ended up considering external structural insulated panels around the building. The decision was made pretty unanimously to proceed with locally manufactured SIPs for affordability, speed of construction, and also penalized system. So we're proceeding with SIPs on the below-grade foundation walls, the wall system, and the roof system as well. In fact, the entire building enclosure except the slab itself. Our below-grade wall assembly is made of the foundation concrete walls and a prefabricated SIP panel comprised of 250 millimeter of monolithic neopor insulation. And so neopor is a type of EPS insulation that contains small black beads of graphite. Graphite help improve the thermal performance of the EPS by approximately 20%. And in our case, neopor insulation helped us achieve higher values with thinner SIPs. We're also using the magnesia board on the below-grade SIPs to protect the insulation after backfill. The magnesia board will help resist the soil pressure on the insulation and also provide some water resistance properties in addition to the drainage layer. The magnesia board on the below-grade panels is offset by approximately 100 millimeter from the edge of the foam, so there is a lap where the panels come together and where the fasteners connect the panel back to the foundations. And actually, by lapping the paneling this way, it allows to reduce the numbers of fasteners and still get a stronger connection of the panel to the buildings. The below-grade SIPs sit on the tray slab edge elements, so the thermal layer is continuous underneath the slab. Installation of the below-ground SIPs is already completed. We used nail seal tape and Passivhaus certified EOT anchors to ensure an airtight seal. The double sticky feature of the nail seal tape allows to pre-install it at inaccessible connections, and it also acts as a compressive gasket. It is airtight and also acts as a vapor retarder. So that's what the fastener looks like. It's adjustable, and the circular portion of the fastener is adjustable as well. The installation went really fast, and all SIPs joints and fasteners were taped prior to the installation of the drainage board. So our above-grade SIPs are not conventional SIPs either. They had to accommodate a solid connection to the steel studs on one side and support the cladding on the other side, and that's where the I-joists came into play. The SIPs are sheathed both sides with the 7/16 OSP with I-joists every 2 feet. The wall panels are effectively non-structural. They're just taking a wind load and some seismic loads on the panels. The SIPs are connected through the I-joists to the steel studs with the stiffeners and fasteners. Oops, sorry about that. So the placement of the steel stud was meticulously coordinated with the location of the I-joist of the SIPs, and sacrificial studs were added as needed. The neopor core is made of multiple slabs, and they're all installed with the staggered joints to account for any risk of shrinkage and avoid large gaps in the insulation if ever shrinkage should occur due to temperature differential between interior and exterior surfaces. And indeed, the multiple small gaps will avoid direct paths between interior and exterior. The wall panels were all pre-manufactured in standard 4x8 elements and are expected to be installed quickly with no waste on site. So let's move now to the roof panels. These were indeed structural, so they weren't just sitting on some other structural structure. The roof panels are built just like a floor system using the I-joists, and the space between the I-joists is filled with neopor insulation. The wall and the roof SIPs panels look the same though, and the I-joist with the one I-joist at one edge and one in the middle and a recess at one end so that they can be connected. When the panels were connected, they share that I-joist, and that's how they nest together. In our passive house planning package modeling, we modeled the SIPSU value in 5 layers, as you see here on the slide. The OSB, the flange, the web, the second flange, and then the second OSB layer. The I-joists are preferable to solid material as they minimize the risks of thermal bridging. And because of the size and the shape of the joints, the air is trapped in the gaps, and there will be no air movement and not a lot of convection in those gaps. So there is an inherent thermal benefit in these joints. Another milestone of energy efficiency is the air tightness. In fact, the thicker insulations ensure fewer energy transfers and less drying potential. Therefore, vapor control and air tightness become very important. Our primary airtight layer is the outboard OSB of the prefabricated SIP panel, and all joints will be taped. And I'm going to note here, I was just listening to the presentation. Actually, the Passive House Institute recommends using 2 layers of OSB staggered joints as an airtight layer. And in our case, we do the two layers of OSB can act as the airtight layer, but unfortunately, we don't have the staggering of the joints. So our primary airtight layer is the outboard OSB of the prefabricated SIPs, and all the joints will be taped. And so the red line here is showing our continuous airtight layer, and at the so at the slab, the 15 mil high-density vapor barrier with taped joints is installed on the tray slab on grade between the 2 layers and will remain continuous along the foundation walls and taped to the inboard OSB for vapor control and outboard OSB for airtightness continuity. So the airtightness at the elevator pit is provided by a self-adhering high-density waterproofing membrane. We're using here the Suprema Colfin ICF. And airtightness at the structural penetrations is maintained by taping to the continuous steel structure elements. Any fasteners, nail penetration is prepped with nail seal tape to maintain airtightness. And from a design standpoint, we minimize the number of plumbing fixtures installed along exterior walls. So all stoves and cooktops have recirculating vent hoods with a charcoal and an aluminum reusable filter. And airtightness at surface penetrations and electrical conduit is maintained via gaskets and tapes. This is a little video taken during the SIGA TechRep inspections showing the great commitment of the trades working on the project.
Sorry, what were you saying? I was just saying, this one here looks great. Not that any of them don't look good. This one looks particularly good because, well, a few reasons. It's pushed into the corner, so you have some angles. You also have some other angles going from the slab up to the side of the foundation as well, but everything is pushed in nice and tight. There's multiple layers of return. You formed your gasket, and I can tell that it's definitely had pressure applied. There's dirt and standing water on here. This is solid. This is perfect right here. I like seeing that, guys. That's perfect. So the whole job is perfect. The whole job.
So all the penetrations in the SIPs are pre-cut and drilled by the manufacturer and spray foamed to ensure continuous thermal layer and sealed for airtightness with SIGA tapes on site. And in this case here, we have also used stainless steel gaskets as well. So construction sequencing and good practice execution tips are all discussed and reviewed at pre-installation meetings and trainings. These pictures show the small mock-up that was built for our second airtightness training session We are training the trades that will interact with the envelope, and we're also testing our details and informing building officials and inspectors on how we're going to achieve exemplary levels of airtightness. Here we're showing the sequencing we're proposing for the installation of our prefabricated parapets. So we plan to first tape our exterior wall weather barrier to the roof SIP outboard OSB. And of course, we're not just taping, we're stapling, then taping, and we've set a stringent staples budget, one staple every 3 feet and at overlaps only. So then the Sega nail seal tape is pre-applied at the wood stud location on the prefabricated parapets. Then the parapet section is taped in place, and finally it's screwed to the roof SIPs. And after that, another patch of weather barrier will be applied at the parapet afterwards, and that's just to meet building code requirement. Has nothing to do with our path of house envelope. Let's move on now to our vapor control strategy. So for vapor control, we follow the basics, our vapor control layer on the warm side of the insulation. So the inboard SIP OSB acts as our vapor control layer. The vapor control layer will be maintained continuous around the envelope, and that's the heavy blue line that you see on this building section. Our Hubert analysis of our exterior wall assembly indicates risks of condensation on our outboard SIP OSB. But we think that with creating a ventilated cavity between the SIP outboard OSB and the cladding ensures the outboard OSB to dry in the summer. And in the winter, since the average temperature are around -16 degrees, there won't be much in the outside air, and it won't be raining. So the vapor diffusion through the assembly from exterior to interior isn't the issue. It's only the interior moist air that's the concern. And therefore, we're planning to ensure an airtight structure internally and seal all the SIP's inner OSB penetrations. UVert analysis of the roof assembly indicates also risks of condensation on our recovery board, and we're hoping to minimize the risk with the exemplary airtightness from the inside as well. These pictures show our strategy to ensure an airtight installation at the brackets, actually a vapor-tight installation at the brackets, and used to secure our structural insulated panels to the steel studs. So we are first applying nail seal tape at the bracket, then it's taped in place, and then it's screwed. At the floors and difficult connections, a transitional strip of Sega maple membrane taped both sides to the OSB is applied to maintain the continuity of our vapor control layer. So we're aiming for excellent air tightness levels, 0.3 air changes per hour, and we hope this will mitigate the risks of condensation in the envelope from interior moist air. So in summary, the principles we followed in finalizing our exterior building assemblies is simple. We'll start with our interior drywall finish. Then comes our fire protection layer from the north and south sides where the limiting distance requires it. Then our light steel structure, service cavity, and steel bracing for seismic protection, all 3 layers in one. Then comes our vapor control layer, which is actually the interior OSB layer of the SIPs with taped joints. Then comes the neopore insulation that acts like a Big Four coat. Then our airtight layer, and actually on the north and south sides where the limiting distance requires 1 hour fire separation, we've added a layer of Typex drywall for fire protection of the foamed plastic insulation. Then comes our weather barrier, our ventilated cavity, and finally our cladding system. So this great exterior wall assembly provides us an R value of R54. And that creates a good surface cavity as well, and meets structural requirements, seismic protection, fire protection, and energy efficiency. For the roof, we've applied the exact same principle, and we're working with a roof R value of R75. Let's move now to our next set of challenges, the openings. Windows, doors, and curtain walls are a problem in a passive house project because their R value is less than a quarter the R value of the wall, and they handle everything the wall is handling, water, air, and vapor and heat. So selecting a passive house appropriate doors, windows, glazing, and a curtain wall system for this project was critical. We specified high-performance passive house certified UPVC windows with the Gallhofer Select exterior door line and the passive house certified Ryco curtain wall system. The suite windows were sized for three purposes: optimizing natural light, quality of views, and balancing heat losses and heat gains. So the triple glazed Gallhofer passive house certified windows are being installed, and the window heads are raised close to the ceiling, again to maximize the quality of natural light. Each window is comprised of two window sashes. The narrower sash is a tilt and turn. The wider sash is fixed on the ground floor and fully operable at the upper floors for more ease in cleaning. And this also avoids thermal bridges related to the installation of roof anchors for the window cleaning. And actually, this option in the window is just a fraction of the roof anchor's price. So a passive house flavor has been introduced to our building elevation with guards at the operable sashes to accommodate the tilt and turn feature of the window and meet the code safety requirement while maintaining the overheating risk to a minimum through good natural ventilation. At the garbage room, we used fire shutters as we were not able to source a fire-rated passive house door. Again, bringing the outside into the common spaces was one of the architectural qualities we were really striving for, and all south, east, and west openings were fully shaded with either exterior canopies or interior solar shades to mitigate any overheating risk. So the opening U value penalty and the east-west site orientation was somewhat mitigated by two strategies: tapping into good heat gain potential and avoiding windows on the north elevations. But it does remain very challenging and problematic to have lots of glass in a passive house envelope. And despite all of our efforts, our heat losses are still 1.6 times greater than our heat gains. So now we've got passive house certified windows, curtain walls, and passive house grade exterior doors, and we're going to just follow passive house design fundamental, connect the thermal control layer of the window to the thermal control layer of the wall, and the air control layer of the window to the air control layer of the wall, and vapor control layer of the window to the vapor control layer of the wall. And at the doors, we had a little challenge with maintaining the continuity of the thermal layers through the thresholds. So our SIP supplier, Cot Lumber, supplied this panel that you see here to be fastened to the concrete and secured in place, and then all the voids are filled with the insulation to minimize any thermal bridging. So in summary, by following these simple passive house course fundamental, we optimized our window doors and curtain wall installation details, and that was quite critical for this project. So we have, in summary, doubled the thermal performance of our envelope components compared to the Ontario Building Code, and by doing this, we're achieving an energy performance 6.5 times greater than the Ontario Building Code. And this without accounting for all the thermal bridging effects that are waived by OBC. And given the high R value we're working with, these little details are very important with those thick insulation layers, managing air tightness and thermal bridge-free detailing was critical. So here we're looking at our total transmission heat losses summary. The heat losses from thermal bridging is at 16% compared to 53% of transmission heat losses from our exterior envelope. And the analysis of our design showed a few weak spots and interesting obstacles to our energy performance. There were essentially around intrusions in our passive house envelope and structural member penetrations and sanitary venting. I will start with the parking and garbage room intrusion into the passive house volume. The parking and garbage rooms on the ground floor were kept outside of the thermal envelope. They did create an intrusion into our passive house volume, and this resulted in additional transmission heat losses through additional exterior surfaces because of the exposed ceiling. Our exposed floor assembly with 242 millimeters of outboard rigid insulation and mineral wool insulation in the steel joist space allowed to minimize the transmission heat losses to only 1% of the garbage room and 1% in the parking area. But the parking and garbage room intrusions also generated a few structural thermal bridges, and these were caused by protrusions of highly conductive structural steel in our envelope. And so we have 3 columns on the outside of our thermal envelope supporting 5 beams protruding our passive house shell. Aerogel insulation was strategically used where available insulation thickness is limited to keep the effect of thermal bridges at a minimum. Thermal breaks were incorporated at critical column beam connections to minimize the transmission through the steel elements and keep the dew point outside the structure. Stainless steel fasteners and Fabrica thermal pads are placed between columns and beams. And this is our detail of the standalone column in the parking. We're using aerogel insulation under the beam, and that's what you see there in orange. And wherever we cannot afford more insulation space. And we're also using thermal pads at the column beam connection, and that's what's shown in green. We're looking at promising psi value of 0.0024 watt per meter degree Kelvin. So this effect the effect of this thermal bridge on our model is insignificant, given that it's very localized. This is a section at the beam above the parking. It has a negative psi value. That means that the U value at the beam is lower than the U value at the floor assembly. And that gives us a credit to our energy balance. So our total bill at the garbage parking area is only $54 per year, and that's still the heating bill for 2 units, so it's not as negligible. And this $54 does include the 2% additional thermal losses from the extra exposed surface area and the 0.2 thermal % from structural penetrations. Another obstacle worth mentioning is our brace footing at the south part of the building to address seismic forces. So given the openness of the entrance lobby and the common room area, it was not possible to incorporate bracing similar to what's being done at every party wall between the suites. The wide dimensions result in poor seismic performance in an earthquake, and the brace frame footing was the most cost-effective option to counterbalance that seismic resistance weakness. So we maintained a continuous 11-inch of insulation around that fin to minimize the thermal bridging effect, and its fraction of our total transmission heat losses is only 0.1%. So it wasn't that bad after all, and this is a very good case where very affordable EPS insulation did the trick. Another challenge is the lack of passive house grade roof access hatches here in North America. So we've optimized the size by reducing it to a minimum and used the Belco access hatch, but it's increased our transmission heat losses by 1.7%. And as you can see here, our interior surface temperature is far from meeting passive house levels at 6.9 degrees. So we've allowed for this thermal bridge in our PHBP model, but we will be adding at least 2 inches of insulation on the inside to mitigate all the risks of condensations. Let's now move to the heating, ventilation, and air conditioning design. It wasn't the HVAC portion wasn't easy. It was quite interesting because of the lack of passive house certified ERVs, and we also started with a few challenges. Mechanical ventilation with heat recovery is a prerequisite of passive house, and there were no commercial grade passive house certified ERVs in North America at that time. And the team was unanimously in favor of a centralized system to minimize penetrations in our envelope, given our air tightness challenge and the innovation to the trades, and to minimize maintenance costs in the long term. So the client also had very stringent requirements. Ottawa Salus required the ability to heat to 25 degrees in the winter and cool to 20 degrees in the summer. We're also innovating, and no one in Canada has done this before, and the passive house standard is substantially different from any other standard. We also wanted to minimize the cost of mechanical to offset the envelope upgrades. So we're considered ventilating through a central ERV located in the basement, and we're supplying heating and cooling through ventilation air with a subsoil glycol loop for several reasons. Saving on capital cost and minimizing equipment and simplifying the maintenance and the building automation system. Our mechanical designers selected the state-of-the-art of ERVs in North America at that time. So we're considering the Temp FRG 1200 with a claimed efficiency of 95% and dual core energy recovery. So that's our unit. Not exactly the conventional passive house unit, and we did pay a 20% penalty on our heat recovery efficiency. Remember, TempF was claiming 95% efficiency, but their testing standards were not as stringent as the Passive House Institute. So I'm going to take a minute to show you the impact of that 20% penalty we received. The 20% penalty on the heat recovery efficiency on a project of this scale doubles the heating demand. For our case, we did need to upgrade our insulation from EPS1 to Neopor, and add an additional 4-inch of insulation at the roof. It was quite brutal, but we were very grateful for not being disqualified from Passive House certification. And to meet Passive House acoustic requirements, silencers have been added to the intake and exhaust ducts. So with this unit not requiring defrost, we initially abandoned the subsoil glycol loop idea until a couple months ago, actually 48 hours before foundation walls backfill, when our engineers recommended installing the subsoil glycol loop around the building and ballparked a saving in our heating demand between 1.6 kilowatt hours per square meter annum and 3.9 kilowatt hours per square meter annum. And that's at least 15 to 30% improvement. And these savings were quite attractive, and the cost was still affordable. So
I love polished music, and that served me I was
hello?
at the age of 14 or 15 writing those numbers. There's nothing polished about that guy. And even when he's doing polished music, it's actually not all that polished. So I just know.
Unmuted. Muted.
Hello?
Unmuted.
Sorry about this, folks.
Okay. Sorry, so for the Salus Clementine project, as you see here on these photographs, we're running 4 loops, approximately 400 meters of geothermal horizontal pipes at and around the foundation walls between 5 feet and 9 feet below grade to harvest ground energy. And all the pipes run back to the mechanical room side where they're connected to a special coil in the ERV. So during summer, the subsoil glycol system takes heat from the outdoor air and transfers it to the underground, which then radiates the heat away into the cool earth. And now that our air is cooled to a comfortable temperature, it is supplied to the ERV. In winter, the system is just reversed, and heat is extracted from the ground using the exact same loop system. Oops. So tempered air is supplied to the ERV, where it's tempered even further through the heat exchanger, and the tempering occurs by extracting the heat from interior still air from the building and supplying air from the geothermal heat exchanger. So in summary, our outdoor air is tempered twice, first through heat exchange with the ground, then through heat exchange with extract stale air. And once it's tempered, it is then cooled or heated as needed by the heating and cooling coils in the ERV unit and supplied through a series of horizontal and vertical shafts to the suites. So air is circulated into the building at a set temperature through the duct system, and the ducts get smaller as we move up through the building. So this gas-fired condensing water heater that you see here provides the heating needed for the domestic hot water and the space heating. You see 2 water heaters, but only one is needed. The second one is there just as a backup. And the system is sized to provide all of the heating. We also have an outdoor chiller that's located on the roof to provide all the cooling. The ventilation air is supplied to the ground floor and upper floors through vertical shafts, and that's what's shaded in gray here. And a constant preset ventilation level is delivered to all suites to ensure the air in the room is renewed with fresh air every 3 hours. So within each suite, the ventilation air is supplied to the combined living spaces and transferred through the suite entry and at the door intercut to the bathroom where it's extracted. Suite ventilation can be adjusted by 30% by the resident to increase the fresh air flow or the amount of heating and cooling to each apartment. We're also installing small silencers at each supply and extract for each suite. So we've allowed for a chiller that in theory we do not need, with an additional rack fan for a second chiller and baseboard heater just in case. We're taking measures because the standard hasn't been validated at this scale. So these are risk management measures that the client has requested to be put in place. So we've insulated all our ductwork with fiberglass insulation and ensured the main extract and intake duct are insulated with a minimum of 75 millimeters of insulation. I will now touch on the impact of the thermal bridging from mechanical penetrations, not necessarily related to HVAC, but essentially around dryer exhaust, roof vents, and roof drains. The most problematic thermal bridge in our case comes from the 1,300 feet of sanitary vents through the roof. And every single fixture had to be vented to the exterior. In a conventional project, the sanitary vent pipes are not insulated. It's not required. And diameters are specified as generic 4-inch throughout. In our case, our mechanical designer went through a laborious optimization exercise of all diameters and all lengths and specified a 1-inch continuous insulation throughout. Unfortunately, this is not enough, and the thermal bridging tag for this is 13% of our transmission heat losses. The heat losses through air convection in the pipes are not negligible. We are looking at using an air admittance valves to mitigate the thermal bridging, but it's not allowed by code. We are in the process of applying for an alternative solution for sanitary venting with the City of Ottawa. We're optimistic, but these innovative approaches take time. But if it does not work, we will add at least another inch of insulation to mitigate this thermal bridging. So let's move on now to the exhaust dryer vents. So at the International Passive House conference this year, I inquired about what's being done in Germany to deal with dryer vents, air tightness, and thermal bridging. And I was told we use dryer closets in Germany with small exhausts. It's quite a clever solution, I thought. No wrinkles, very sustainable, brilliant. I also asked our friends from Vancouver, and the response was easy. Use condensing dryers. But unfortunately, after consultation with the client, it appeared obvious that the cultural move to drying closets in Canada was not easy to sell, and coin-operated condensing dryers are not available. So conventional dryers became mandatory, and we naturally specified commercial-grade magnetic dampers for air tightness. For the thermal bridging, we tried to minimize the length of ducts, but it was not straightforward. We have fire-rated assembly at the garbage room, and fire dampers are not permitted for dryer vents by code, and we had to provide a fire-rated shaft in the garbage room to accommodate the dryer ducts. So avoiding the route the dryer exhaust vent through the passive house volume allowed us to avoid 1,632 kilowatt hours per year of transmission heat losses. Mitigating the thermal bridging on the roof drainage pipes was also successful. We have 15 meters of roof drainage pipes. In a conventional building, only the first 3 meters of pipes and the exposed portion of the drain is insulated with 1-inch insulation. For Salus Clementine, the roof drain sump, all horizontal and vertical piping and all elbows are insulated with 1-inch fiberglass insulation. But this is not enough. With the input from our certifier, we also specified an airtight and watertight P-trap at the main trunk at the rainwater pipes to mitigate air convection effects. So P-traps allow water to flow through when it rains, but are normally closed, so wouldn't allow warm air to escape and would effectively mitigate convection effects in these pipes. So the heat loss will be negligible. We have also increased the insulation to 2 inches from the roof drain to the P-trap, and thus result in a negligible effect on our overall transmission heat losses. So to summarize on this thermal bridging part, the major thermal bridging issue is the stringent code requirement for roof venting at all plumbing fixtures. Building codes continue to play a big role in what we build and are allowed to build, even if it's passive house. And we've accounted for this in our PHPP, and we're still reviewing solutions with our building officials, such as using an air admittance valve at the roof penetrations. So let's now touch on the construction contract administration piece. Finishing a project on time and on budget remains one of the most difficult goals to accomplish. In fact, every unforeseen condition becomes a matter of time and dollars. And during these first few months of construction, we had to deal with a couple interesting unforeseen conditions that I'd like to share. So on the first week of August, Ottawa experienced record heat waves with the temperature well above 30 degrees for several days in a row. And this coincided with the spray foaming of all penetrations and joints. Spray foam does not expand as well at temperature above 30 degrees, so additional supplies of spray foam were needed to meet the schedule. And that's why you see a patchwork of spray foam colors here on this slide. And this heat wave triggered thunder showers. So the next few days that coincided with the taping of the header slab vapor barrier. The job site closed for the day and taping resumed the next day, but it still failed because the poly was not 100% dry and the humidity index was quite high, and the taping was performed simultaneously with the backfilling of the edge insulation via telebelt, and fine particles of sand in the air affected the adhesion of the tape, and remedial work had to take place. So in future project, I would say we would need to build a temporary catch basin within the insulation and build in a gentle slope so water can be collected much faster and easier. Our adventure with the thunder showers continued during the basement slab pour. Our 3-inch insulation layer protecting the poly was literally floating between the poly and the concrete reinforcing, and this little video captures it very well. So we had a little pool under our insulation. So we had to use a lower slab concrete mix to handle the added moisture, and the slab was poured continuously on one side, and its weight pushed down the insulation and displaced any remaining water to the surface, which was pumped out. Small cutouts, as you see here, were made in the top insulation layer to facilitate and improve the suctioning. So all these cutouts were then filled with spray foam insulation. And so we used the plywood concrete forms for the concrete foundation walls, and these generated some irregularities in the concrete foundation walls, creating a gap up to a 1/4 inch between the SIPs and the concrete. So we had to use spray foam to kind of compartmentalize and reduce the risks of heat losses through convection effects. And this brings me to the end of my presentation. We're all very proud that our PHPP model verification sheet confirms passive house compliance. And even if the economics indicate that it's the exact right approach, it wasn't easy to start something new with affordable housing where the budgets are naturally tight and the learning curve is steep. We're looking forward to hearing the feedback of the client and user group. I think the plaque will translate a high caliber of efforts, but it will remain superficial, and user feedback will be key to validate our work so we can see it proliferate. Thank you.